Hello lovelies, in this video Brilliant Charlotte is going to be taking you through my predicted paper for Edexcel AS Chemistry Paper 2. This is the predicted paper for 2023. Now, if you haven't had a go at this paper already, what I want you to do is to pause after the question comes up, have a go at it yourself, and then play the video and go through the answers with Charlotte.
Hiya there and welcome to this paper. So today we're looking at the AS Chemistry Edexcel Paper 2 for Core Organic and Physical Chemistry, and this is Primrose Kitten's predicted paper 2023. My name's Charlotte and I'm going to be taking you through this paper and explaining to you how to do all the questions. Let's have a look at question 1. So here we've got a diagram which shows a Maxwell-Boltzmann distribution for a sample of gas at fixed temperatures. EA is the activation energy for the decomposition of this gas. And we're asked to illustrate on this diagram a new distribution for the same sample of gas, but this time at a higher temperature. So here we need to understand how it's going to look different to what we've already got. Okay, so what we need to know is if it's at a higher temperature, we're going to have a similar curve, but it's going to be slightly displaced to the right. It's still going to start at the origin because basically there's 0 molecules that have 0 energy, but it's kind of going to have the same area, but it's going to be more stretched out. It's going to be a bit lower than the existing curve, okay? So the new curve is still going to start at the origin. The peak is going to be lower than the original, and it's going to be to the right, all right? So here we're going to have a go. So it's going to look something like this, and then down to there. So there, it's clearly to the right, the peak still goes through 0, 0. It only passes through this curve once. It doesn't like start underneath the curve and then end underneath the curve. Its end point is going to be higher than the start there. And yeah, sort of overall there, we can imagine with all those allowances, the area underneath should be about the same. But the key point here is that when we have this higher temperature, there's going to be more molecules and energy above that activation energy. And we can see that there due to the fact that the area underneath the curve and above the activation energy for this curve at a higher temperature that we've just done is bigger, okay? So we've sort of referenced this now, we're asked to describe what the area underneath the curve represents. And that is the total number of particles present. And that's exactly why the total area underneath these two curves at different temperatures had to kind of balance out as being more or less the same. Because if they didn't, it would imply that there's a different amount of molecules, which would change everything. But here, so we're just going to write that the area under the curve represents the total number of molecules present. So total number of molecules present. So now we're told that the rate of a chemical reaction may be increased by an increase in reactant concentration. So also by an increase in temperature and by the addition of a catalyst. And we're asked to state which, if any of these changes, actually involves a different activation energy. And only one of these do. The one which does is that addition of a catalyst. And that is how it works. So a catalyst, the way that it works is it provides an alternative pathway for the reaction that has a lower activation energy. And because it has a lower activation energy, that means that we're going to have more particles which have an energy above the activation energy. Okay, so it's an alternative route, I'll write it just here, an alternative reaction pathway with a lower activation energy. And therefore that means that more particles will have an energy above that activation energy. Perfect. Okay, let's have a look at the next question on the next page. So here we've got a multiple choice question. We're asked to select the Maxwell-Boltzmann energy distribution diagram, which shows the increase in temperature from T1 to T2. Okay, so that's this higher temperature that was just talked about. So here we need to have a look at these and we need to think, well, which of these is going to show that? Well, kind of like our answer from the earlier question, we know that when there is a higher temperature, the areas underneath them need to basically work out the same, but the higher temperature is going to be shifted to the right and it's going to have a lower down peak. So the answer to this one is C. So here we're told that the bromine test can be used as a qualitative test to determine the presence of unsaturation in 2-butene. And what unsaturation means is the presence of alkene bonds. So we're asked here to draw the structure of the E and Z isomers of 2-butene. So the very first thing that I would do is I would draw out butene, not worrying yet about whether it looks like an E or a Z isomer, and we'll just start there. So initially, we know it's got 4 carbons in a row, and because it's but-2ene, we know on the second carbon we have a double bond. So if we were to sort of fill this in just in a normal boring diagram, it looks like this. So next though, we need to translate it into this E and Z stereoisomers. So what I'd always recommend with these that we do is we draw the central C double bond C and make it look a little bit like ethene, whereby we can circle off the groups attached to each of those carbons of the carbon double bond, and then sort of attach those in the relevant places over on our molecule. So here we go, this is how I have redrawn it. The only reason why I do that is because I feel like it's much more visually understandable to be able to say which is the E and Z isomers. So E isomers are essentially trans isomers. So that will be when the same group is on opposite sides of the CC double bond. So what I've just drawn here is actually the E isomer. So I will fill that in the space that they want. And then the Z isomer is the same as the cis isomer. And so that is when we have them on the same side of each of those carbons. Doesn't matter if you do the H's on the tops or bottoms, it will work out the same either way. Next, we want to state the meaning of the term stereoisomers. So this definition, not only is it good to know for these questions, but also just for your understanding of what a stereoisomer is. So what a stereoisomer is are a set of molecules that have the same structural formula but whose atoms are arranged differently in space. So here, if I was to define stereoisomers, I'll write it over here for you. I would say that they are molecules with the same structural formula, so molecules with the same structure, but with a different arrangement in space. And those are your 2 points that you need to know to be able to get these definition questions correct for a stereoisomer. And at this level, we only really know about cis, trans or EZ stereoisomers. In the second year, if you're a student that's currently in the second year of A-level, you'll be familiar with optical isomers as well, which are also an example of a stereoisomer. But that's our perfect definition for what a stereoisomer is. So now, using the curly arrow model, describe the mechanism for the reaction between Br2 and this 2-butene. And it doesn't matter which version we use, it's not going to matter. So, first things first, I will draw one of our iterations of the but-2ene. And then the next thing I will do is I'm going to show bromine sat next to it, but polarised. And remember that this CC double bond is a region of high electron density, so it is able to do that. So Br minus, Br plus. Now what we want to do is to show the movement of a pair of electrons from this CC double bond to the delta positive bromine, and from the bond between the bromines to the delta negative bromine. And what that will then do is it's going to form an intermediate where we have a carbocation, and we also have now formed a bond between one of these 2 carbons and the bromine. We've also, due to the movement of the pair of electrons between the 2 bromines, we have formed a negative ion. So the final step of this is the movement of the electrons in that bromide ion towards that carbocation. And that forms that final bond that we need to have finished this mechanism. So there we go. Pretty perfectly done, I think. Lovely. And the great thing is that particular mechanism is going to look the same whatever alkene is needed. Remember, all the groups coming off of it, they're not going to impact on this basic structure that we have every time we see one of these electrophilic addition mechanisms. Perfect though, let's see what the next question is. So here we're asked to calculate the atom economy for the formation of 1-bromobutane in this reaction. And so first things first, we need to remember how we calculate atom economy. And atom economy is like the mass of the useful product divided by the mass of all the products. So here we can see, we can work out what the mass of these things are, okay, or the MRs of these things. So in terms of the mass of the useful products, we know that the useful product is what we're making, 1-bromobutane. So the MR of 1-bromobutane, they tell us, is 136.9. Now all of the products includes that, so we'll sort of write that down first, but then we also want to add on the other things as well, all right? So that means we've got KHSO4. K is 39.1, H is 1, S is 32.1, oxygen is 16, and we've got 4 of those, so that makes 64. And then finally there we've got an H2O as well, and H2O is 2 hydrogens plus an oxygen, so in total that is 18. So if we tally up all of that there on the bottom, we end up having 136.9 over 291.1. And because here you can see all of the answers are in percentages, we're going to turn this into a percentage by timesing it by 100. Normally atom economy is given as a percentage. So here that's just the same as well. So if we tap that away into a calculator, I make that 47%, which if we look at the answer options, you can see that that is A. So next we're told that one molecule of an alkane X, so it's important we know it is an alkane, can be cracked to form one molecule of heptane and one molecule of cyclopentane. And we're asked to work out then, well, what would be the molecular formula of X? Now when we do cracking, we basically split up that molecule into several other ones. Everything is conserved. So here we've got X is going to get cracked to make heptane. So here we're really getting tested on, well, what is heptane? Heptane, as it ends in an ane, we know it's an alkane, and we know that the general formula of an alkane is CnH2n plus 2. So if hept refers to 7 carbons, we know that we have C7H16. So we know that the alkane X is going to get cracked to make C7H16 and then also cyclopentane. So we should also know that for cycloalkanes, the general formula is CnH2n, which is exactly the same as alkenes. So if it's cyclopentane, we know that pent refers to 5 carbons, so that would be C5H10. So here, because they say that only one of each of those is made, we can simply add up the number of carbons and the number of hydrogens to get X. So X is going to be C12H26, and that there is A. Okay, so in question 3, we're told that we have 4 alcohols, all of whom are isomers, and they have the same molecular formula as isomers would, of C4H10O. Now we're told that one of the isomers doesn't react with acidified potassium dichromate. Well, that bit of information tells us that we don't oxidise that isomer, and the only type of alcohol that we can't oxidise is a tertiary alcohol. So those are the clues there that we have. So we're told to name the structure of that particular isomer and to name it. So here we need to think, okay, how can I get the isomer of C4H10O, which is an alcohol and which is a tertiary alcohol? So with that, whenever we have tertiary, that assumes to me that we're going to have lots of branching and things throughout it. So if we try 3 carbons here in a row with a little methyl branch coming off of it, and then to that we put the OH group on the middle carbon, I can see straight away there that I do indeed have a tertiary alcohol, and that is because I have a carbon that has an OH attached to it, and that carbon is also attached to 3 carbons. So that there tells me that I have a tertiary alcohol. So then we're asked to name this particular isomer. So here I can see that there are 3 carbons in a chain. So I know that it's going to be propanol. And I also know obviously it's an alcohol, and that is on the 2nd carbon. So it's going to be propan-2-ol. And also I know it has a methyl group as well. So that methyl group is on the 2nd carbon. So that means that the name of this alcohol is going to be 2-methyl propan-2-ol. And that is our answer. So for 3.2, we're told that the infrared spectrum of one of these alcohols is given below. Identify one feature of the infrared spectrum which supports the fact that this is an alcohol. So here, if we look at this, we can see that we have a peak in the range of 3,230 to 3,550 centimetres to the -1. So that reason there is enough to support the idea that an alcohol is present. So here, when we are asked to express it, I would be specific at the range. Now, I would sort of use your data sheet to get that range, sort of exactly the relevant range to an alcohol. But I would state in my answer that the infrared spectrum shows an absorption peak, and then I would be specific as to where that is. So 3,230, 3,550 centimetres -1. Never forget the units. And then we're going to say that is an alcohol peak. Perfect. So that's a great question. Really, really important that we can do questions like that. And it's just making good use of the data sheet. They don't expect us to have all of these memorised at all. We just need to get savvy and know what these main peaks are on an infrared spectrum. So here we've got quite a long mark question, 6 marks. And in this question, we're asked to explain the solubility of the following compounds in water using your knowledge of intermolecular forces. And here we've got methanol, butanol, and octane. So comparing those, I can see I've got 2 alcohols of different lengths of their chains, and I have an alkane as well. So I would start just by realising what I'm dealing with here, and then use that to sort of support my answer. And it's 6 marks, so I would imagine I'm probably going to get a couple of marks for talking about each thing. So one general thing I can say, or a couple of general things I could say in this question, is that these alcohol groups or hydroxyl groups are polar. And we know they're polar, don't we? It was due to that difference in electronegativity within the bond. And when we have polar bonds, that does promote hydrogen bonds forming and therefore solubility in the water. Carbon chains, on the other hand, are non-polar, which means that they are less likely to be soluble in water. So we could start just by writing down those just general facts, that hydroxyl groups are polar, and then therefore that fact is going to promote solubility with water, the formation of all of those hydrogen bonds. And then on the other hand, when we just have carbon chains, so no hydroxyl groups, these carbon chains are non-polar, and therefore they are going to resist the solubility. Okay, so now if we were to break these down bit by bit, like I originally suggested. So if we start with methanol. Now methanol is going to be soluble in water. If you think about what we said, it has that hydroxyl group, which is polar. So we know straight away that it is soluble. Here's something that we could say as well as it being soluble in water is just talking about those intermolecular forces that the question said it wanted. I'm going to say that it forms hydrogen bonds with the water. So another thing that's important with this, because of course we've got butanol to talk about shortly too, is that because methanol is particularly a short chain alcohol, you are still going to have areas in alcohols that are just carbon chains, but because this is a short chain alcohol, that OH group is going to have a more dominant effect and therefore forms those hydrogen bonds. And we're going to see in a minute that that's going to be compared to butanol. Methanol will be more soluble. And that's because it is a shorter chain, so that means that that hydroxyl group, which is polar, is going to have a larger effect. Okay, so now let's have a look at butanol and say something a bit about butanol. So butanol is soluble, but it's less soluble in water. So we're going to say that it's slightly soluble in water. And that's because we have more of a balance this time, that it's a longer chain molecule between those polar hydroxyl groups and the non-polar carbon chains, kind of like they're opposing each other. So we've got 2 opposing solubility trends. If we think about what we just said in the introduction, we've got those polar hydroxyl groups but then we have the non-polar carbon chain. And as a result there, it is going to be less soluble than methanol. Finally, now we can talk about octane. So octane doesn't have any hydroxyl groups at all. It is just an alkane, and therefore, as a result of that, we can say that it is insoluble in water. And that's because it is just a long chain alkane. And of course, sort of back to what we said earlier, when we have those long chain alkanes, they're non-polar, which means that we're not going to get any particular interactions with the water there. There's going to be no hydrogen bonds forming. Perfect. So that would be the answer to that one. I hope that made sense. Let's have a look now at the next question. Okay, so the correct order of boiling points of primary, secondary and tertiary alcohols. So a similar idea here, but this time instead of solubility, we are talking about boiling points. So here it's still about the interactions between these molecules, okay? So basically it's saying which of these has the strongest intermolecular forces, because the one with the strongest intermolecular forces will need more energy to break them, and therefore they will have the largest boiling point. So what we need to ask ourselves here is which has the strongest intermolecular bonds? Is it primary, secondary or tertiary alcohols? So what we need to know is that a primary alcohol, something like butane 1-ol, has a much higher boiling point than a secondary or a tertiary. And the reason for this is that the OH in a primary alcohol is much more exposed than when we have a secondary or a tertiary alcohol. So if we have, say, a secondary alcohol, there's all these other groups surrounding it, and it is far less exposed. It is harder for it to form those hydrogen bonds with other substances, such as themselves, and therefore that is why we end up having a higher boiling point for the primary alcohols than secondary and then tertiary alcohols. So the answer to this one here is A. So next, we're told that compounds A and B both have the same molecular formula, C3H8O. When A and B are reacted separately with acidified dichromate, we're told that A becomes C and B becomes D. And we're given an infrared spectrum of C, okay? So what we can see in this diagram here is C. So let's look at the next question. We're told to name and draw the structures of A and B. So in order for us to do this question, it really requires us to have a think about the information that we've been given. We know that A became C, we know that B became D, and we know that the molecular formula of the A and the B is C3H8O. Okay, so it's likely some sort of propanol from that information. From the infrared spectrum that we saw, we can see that after we oxidize it with this acidified potassium dichromate, we didn't get any broad peaks in the 3000s, okay? What we did get though is a little sharp peak at around 1700. And that information together tells me that C is going to be something like a ketone or an aldehyde. It's just going to have a C double O group, but it is not going to have an OH group because it doesn't have that broad peak in the 3000s. Now that information tells me that A must be a secondary alcohol because when we oxidize it with acidified potassium dichromate, we only partially oxidize it to that, say, ketone or aldehyde. And if that was the case, it would be a ketone in this case. So I would suggest that A is actually a secondary alcohol. And from what we just said, that C is probably a ketone. Now, from what we were told earlier, the secondary alcohol's already been addressed now. So that means that B must be the other kind of alcoholic isomer, which here in this case is very likely to be just a normal primary alcohol, which would mean that D would likely end up being a carboxylic acid if that was also oxidized with acidified potassium dichromate, because you can fully oxidize a primary alcohol. So for that reason, with the formula that we have been given, I would say that structure A is a secondary alcohol, which means that it is on the second carbon of this propanol, which means that what we have here is propan-2-ol. And on the other hand, structure B, we said that that is likely going to be a primary alcohol, and therefore that means that structure B is likely to just be propan-1-ol. So a carbon is going to be on either end of this molecule, on the first carbon of the chain. And that there is propan-1-ol. Okay, so next we're asked to draw the structure of C, and we've already determined that C is a ketone. We know it's a ketone that's derived from a 3-carbon alcohol, and we're also asked to explain fully how we arrive at this structure. Well, first things first, let's draw the structure. So propan-2-ol would be oxidised to form propanone, which is a 3-carbon ketone. And we're asked to explain fully how we arrived at this structure for C by using that infrared spectrum. And we discussed this before, it's because the infrared spectrum shows no broad absorption in those 3000s. And I would be specific at this point. I would go to my data sheet, look up where that C double bond O is for ketone and where the OH is for carboxylic acid. And I would write down those numbers, okay? So infrared shows no broad absorption between 2,500 to 3,300 centimetres -1. Don't forget the units. So that means that it is not a carboxylic acid. However, on the other hand, it does show a peak at 1,700 centimetres -1. Again, don't forget the unit. And that we know is due to the C double bond O group. So here, because we know it's not a carboxylic acid, and we know it does have a C double bond O group, and we know that this is due to like a partial oxidation, that means that this must be a ketone. And that is how we've determined that structure. Okay, so back to B now. We're asked to write an equation for the reaction of B with acidified potassium dichromate. And generally with these oxidation equations that they ask us to write, they want us to use square brackets O to represent the oxidizing agent. So we're not going to put in potassium dichromate formula in this at all. What we're just going to do is to have the formula for that propan-1-ol that we decided B was. So that is going to be CH3, CH2, CH2OH. And because we're oxidising this fully, we're going all the way to a carboxylic acid, we're just going to add 2 oxidising agents because the first oxidation makes an aldehyde, and then that second oxidation makes a carboxylic acid, and then we will make that carboxylic acid of CH3, CH2, COOH. And then we also make a water during that oxidation as well. So this here would be the formula that they would expect you to do for this. Finally, for D, they want us to describe a test to distinguish between C and D. So that means they want us to distinguish between a ketone and a carboxylic acid. And a great test for this one would be the test which is the 2,4-DNPH test. Because what that test will do is when we have a ketone present, we would get like a nice orange-red precipitate formed. And when we carry out the exact same test for carboxylic acid, we wouldn't see this. So this here is going to be our test result, okay? So we're going to use 2,4-DNPH, and for a ketone, we will get an orange-red precipitate. Perfect. So let's have a look now at the next question. So here we've got like a mathsy question here. We're told that the heat change associated with the dissolution of NX solid was calculated using the following method. So 100 centimetres cubed of distilled water was added into a polystyrene cup. The initial temperature was 36 degrees C. So then 0.5 mole of MX solid was added to the water and it was stirred continuously. It was observed that the temperature of the solution decreased. Now that's really important. And the lowest temperature measured was 17 degrees. Density of water is 1 gram per centimetre cubed and the heat capacity is 4.20. So in this question we're asked to calculate the amount of heat that should be supplied to bring the system back to 36 degrees. So whenever it's a question about heat energy, we're going to use Q equals mc delta T. So M is the mass of the thing that's getting heated up. So in this case, we've got distilled water. We're not quite given a mass. We're told the volume of the water is 100 centimetres cubed, but we're also told its density is 1 gram per centimetre cubed. So actually the mass of that water is going to be exactly the same, but in grams. Okay, so the mass of the water is 100 grams. C is the specific heat capacity, which we're told is 4.20. And the change in temperature, we need to think the temperature decreased down to 17 degrees C, and then it's gone back up to 36. So the change in temperature will be 36 minus 17, will end up giving us 19. So now we know the mass, the specific heat capacity, and that change in temperature, we can work out what Q is, okay? So now it's going to be Q equals 100 times 4.20 times by 19. And if we put that into the calculator, we end up getting, sorry, I haven't gone anywhere. Here I am, okay. So we end up getting an answer of 7,980 joules, all right? We could there change the units to kilojoules. They haven't specified the units to use for this particular question here. So either we could say 7,980 joules, or we could say 7.980 kilojoules. Okay, so in 4.2, we're asked, is the dissolution of MX in water an endothermic or exothermic process? And we're asked to explain our answer. So the important bit here is a word I've previously circled. It's the fact that the temperature decreases, okay? And if the temperature decreases, that means that the process must be endothermic, because we need to remember that if something's endothermic, it means it's absorbing energy from the surroundings, and that is what brings down the temperature of the water, because it's getting absorbed into this reaction, which is an endothermic reaction. So our answer here is going to be endothermic, and our explanation is that the reaction there has absorbed heat energy from the water. Okay, lovely. Okay, so next we're asked to calculate the enthalpy change associated with this reaction. And we need to remember that enthalpy change is the energy per mole, okay, of that reaction. So we've already worked out how much energy was released, and we need to divide it by the amount of moles of whatever fuel took part in that reaction. So we know that we had the 0.5 moles of MX, and that was the thing which actually reacted there to cause that change in temperature. So one thing to remember here, we want the enthalpy change to be in kilojoules per mole. Now here, this is when it's important that we use the Q, which was in kilojoules. If we didn't write that down for part 1, that's absolutely fine. We would just convert it here by, again, dividing the joules by 1000 to get an answer in kilojoules. So we're going to say it's 7.980 divided by the moles of that fuel, and in that case that is 0.5. And the answer that we get there is going to be 15.96 kilojoules per mole. And that there will be our answer. Now before we move on to the next question, I do want to point something out here. Whenever we have an enthalpy change calculation question, which involves this calorimetry, so these changes in temperature, whether they're increasing or decreasing, we do want to finally think, did that temperature increase or decrease? Because if the temperature increased, that means it's an exothermic reaction, which means it has a negative enthalpy. Whereas if it's exothermic, like this, because the temperature has decreased, then that means that it's a positive enthalpy. Now, the reason why it's important that we know that the enthalpy change is positive or negative is if it was negative and we didn't write it down, we would lose a mark in our answer. Obviously in this case, it was positive, so it's really not the end of the world. But I don't want to just glance by and not point that out, because to be perfectly honest, I think majority of the time it ends up being an exothermic reaction just so they can test you on that marking point. So really keep an eye out for that. Let's have a look at the next question then. Okay, so this one talks about kerosene. We're told it's used as a fuel for aeroplane engines, which it's obtained from crude oil. Okay, so we're asked to name the process we use to obtain kerosene from crude oil and explain why the process works. Now, this is a process that you should be familiar with even from GCSE, okay? It's quite a commonly talked about process. And the process which does separate kerosene as well as other fractions from crude oil is called fractional distillation. And fractional distillation relies on the fact that all the different fractions, for example, kerosene or petrol, have different boiling points. And that is how we can separate them. Perfect. Central heating fuel contains saturated hydrocarbons with the molecular formula C16H34. Now that is an alkane that is talking about. And we're told that it's employed in determining the cetane number of diesel fuels. We're asked to write an equation for the incomplete combustion, so really important there that we need incomplete combustion of C16H34 to produce carbon monoxide as the only carbon containing product. So here we need to remember that incomplete combustion, just like complete combustion, involves that C16H34 or whatever the fuel is reacting with oxygen in this combustion reaction to make, if it's incomplete combustion, carbon monoxide is often made. Sometimes carbon is made. Sometimes a bit of carbon dioxide in conjunction with these other substances is made. And we will also produce water, vapour, okay? So here, because they say carbon monoxide is the only carbon containing product, they narrow it down a bit. If they just said write an equation for incomplete combustion, actually you could do lots of different permutations of carbon dioxide, carbon monoxide and carbon along with that water, because it will really just depend on how much oxygen was present to enable that combustion. But in this question, we know it is carbon monoxide, and like we mentioned, water also gets made. So in this question here, what we need to do is to balance it now. So we know that we have 16 carbons there, so we're going to put a 16 in front of the carbon monoxide. We also know we have 34 hydrogens. So over here we've got H2s. So we need 17 H2s to make 34 hydrogens. And then overall here we need to have a look and a tally up of how many oxygens we have left. So we've got 16 there and 17 here. So 16 plus 17 ends up giving us 33 oxygens. So that must mean that if we have 33 oxygens and we halve that number, we end up getting how many O2s we're going to need. And that is going to be 16.5 O2s to balance this equation, which is just 33 divided by 2. So that there is our equation, nicely balanced. So next up here we have a little multiple choice question. We're told that 62 milligrams of which hydrocarbon undergoes complete combustion to give 88 milligrams of carbon dioxide and 54 milligrams of water as the only product. And we're told that the relative molecular mass of the hydrocarbon is 62. Now the way that I would tackle a question like this is I would start by trying to write like the balanced equation, but by using algebra. Don't want to scare you there, but I would sort of say, oh, we've got XC's and we've got YH's, and we know that if we add a certain amount of oxygen to that, which we don't know how many yet, we're going to get CO2, and let's say we're going to have X of those, and we're going to have some H2Os, and remember, because there's two H's in the H2O, it's basically going to be however many there are of Y halved. Okay, the oxygens I wouldn't worry about balancing because we don't have any information about the oxygen in this question, so it doesn't really matter. Now, the reason why I've done this, you might be thinking, well, this is madness, why am I doing this? But the reason why I'm doing it is if we then can write down these masses that we have, so we know we've got 62 milligrams of the hydrocarbon, we know we've got 88 milligrams of carbon dioxide and 54 milligrams of water, then for the MRs, we're told that the MR of this hydrocarbon is 62. We are told that carbon dioxide, well, we're not told, but we know if we added up one carbon and two oxygens, we get 44. And water we know is 18, it's MR. Now we can work out what the molar ratios of those are now. Remember, it's not technically the actual amount of moles, So we don't want to call it moles necessarily, but it's certainly something proportional to the amount of moles. So we know we get 1 mole of that hydrocarbon we're thinking about. We get 2 moles of the CO2. We end up getting 3 moles of the H2O. Now that's important because if we know that those moles are relating to the amount of carbons there are, or like carbon dioxides that there are, we can do this little comparison then and say, okay then, if that's the case, if I've got 2 moles of this carbon dioxide, then I must have 2 moles of carbon. So our X in this case, which is going to relate to this, is 2. Likewise, we can do the same thing here for the waters. We know that we've got 3 moles of water, which must mean that we have 6 moles of H2O because there's 2 H's in every 1 water. So then we know that we have 2 carbons and we have 6 hydrogens. So our answer here is going to be B. Okay, so here we're told that C16H34 is cracked to produce ethene, but-1ene and octane only. The hydrocarbon but-1ene belongs to the homologous series, which has structural isomers. So here we're asked to draw all of the structural isomers and to label them. So with these, I would recommend that you're just very, very methodical with it. So I would always start with saying, okay, let's just do it in a straight chain. And because we know it's got a double bond, let's attempt just to put that double bond bang in the middle. Now this isn't going to have any stereoisomers because around that double bond you can see already that certainly over here we've got just 2 of the same groups attached to that carbon of the CC double bond, which sort of violates one of the conditions we know we need to have for stereoisomerism. So this is one version, and this one here is going to be called but-1ene. Then on the other hand, sticking with what I said about being methodical, see I have this one version here which has the double bond on the first carbon. Now I'm going to still do a straight chain, so 4 in a row. I'm going to put my double bond on the second carbon. So by doing that, I end up with something which actually will have stereoisomers. Okay, so obviously this is going to be called but-2ene. Also, we can be more specific with this because see, around this CC double bond, each of those carbons of that CC double bond, you have 2 different groups attached, all right? You've got a CH3 group and an H group. And that's true on both carbons of that CC double bond, which is what we need to have for this stereoisomerism. So in this particular case here, if we remember that we can have cis or trans, what we have here is a cis isomer. So we can call this one cis but-2ene. And then that leads us to our next isomer, which is going to look much the same, except instead it's going to be the trans isomer. So we want those groups, those identical groups, to be on opposite sides of the carbon. So see here that we have got these hydrogens opposite each other. So that there is going to be called trans but-2ene. So we've still got 1 more to go because obviously here we've done all of these 4 chain length carbon alkenes. All of these alkenes with 4 carbons in their chain. But there's another thing we can do here. We could also shorten it just to be a 3 carbon chain, and I'll write this one in here. So we can still have a double bond on there. But imagine we have branching, and instead on that second carbon, we have a carbon chain branching out of that. So it still looks very, very similar to what we have before, except it isn't a butane. It isn't a butene anymore. Instead, it is a 2-methyl prop-1ene because the longest carbon chain in this, which is 3 carbons, the double bond is on the first carbon of those 3 carbons, and then we have a methyl group on the second carbon of it. So there you go. Those are the 4 different isomers for this. So next we're asked about alkane fuels which get burned in petrol engines, and we're told that they can produce 2 toxic gases, NO and CO. And we're told here that catalytic converters are used to remove those gases. We're asked here to write an equation for the reaction between carbon monoxide and nitrogen monoxide in a catalytic converter. And what happens is the carbon monoxide reacts with nitrogen monoxide to make carbon dioxide and N2. So this is going to need a bit of balancing. So we need 2 carbon monoxides, 2 CO2s, and 2 NOs. And this is very important that we understand how this works. Obviously, we start with 2 toxic gases and we end with carbon dioxide, which is not toxic. It's not ideal because, of course, it does contribute to the greenhouse effect and global warming, but it doesn't have that direct effect of it being a toxic gas released into the atmosphere. And nitrogen, which is just an inert gas, which makes up 78% of the atmosphere anyway. So that's absolutely fine there. So then for B, we're asked to identify the catalyst used in catalytic converters. And there's a few options that you can say here. Okay, so there's platinum, there's also palladium and rhodium. So I'm going to write down here platinum. I would recommend that you write down whichever one you're most familiar with and you feel like you recognise it being taught. So palladium or rhodium are also good options for that. So next we're told to give the stages that take place in a catalytic converter to allow carbon monoxide to react with nitrogen monoxide. And I really like these types of questions. They are pure recall and they're very structured in their story as to how it works. So I'm going to do this in bullet point form because it really illustrates what we need to know. And if you're not familiar with this, perfect for a flashcard. So we're told here that carbon monoxide and nitrogen monoxide are adsorbed, not absorbed, adsorbed onto the surface of our catalyst. Okay, now adsorbed means it kind of sticks to the surface of that catalyst, not absorbed. It doesn't become a part of it, it doesn't go into it. It just purely sticks onto the surface of that catalyst. So that is very much our key word in this question. And this marking point in particular, you would not get unless you use that word correctly. So the next bullet point to state is that now we get a weakening of the bonds, which lowers the activation energy. So bonds are weakened and the activation energy is lowered. So then finally, the final marking point here is that the 2 products that we make during this reaction, the carbon monoxide and the nitrogen, desorb. So another really important word there, desorb from the surface. Okay, so not adsorb, not absorb, they desorb, and that's kind of meaning unstick from the surface and go out into the atmosphere. Desorb. So in that word, when we're talking about how a catalytic converter takes place and how it works, in these types of questions where we need to talk about catalytic converters and how they work, those are 2 key words that they need to see in your answer. Adsorb, talking about the reactant molecules sticking to the surface of the catalyst, and then desorb when the products leave. Okay, so here this is a fun one. We're given an enormously long word. 3 bromo, 1 chloro, 4 ethyl, 2,5-dimethyl, hep, 2,5-diene. Whew! And we're asked here to identify which of these are it. Now, I'm going to use a process of elimination here to get us really started. I can see, because it says diene, I know that I need to see 2 C-double-C bonds, 2 alkene bonds. And straight away I can see D does not feature that. So I'm going to get rid of that straight away. I can also see in the name that it's got chloro in it, which means it's going to have a chlorine. Now A and B both have a chlorine, but C doesn't. So I'm just going to get rid of C there. So now I am stuck between those 2 things. And at first glance there, you can really see actually that they look quite similar, don't they? There's nothing massively dramatically different about them. We can see on B that we have 2 methyl groups. Let me highlight them. But we don't have that on A. So if we look back at this name here, I can see it does indeed say 2,5-dimethyl, which means 2 methyl. And so that to me tells me that our answer must be B, because A just doesn't have any methyl groups. So there we go. That would be the answer to 5.6. The answer is B. Okay, so this question here is about the percentage atom economy for the formation of the chloroalkane. And percentage atom economy is going to be worked out using the MR of your useful or desired product, which in this case they have said that we're making the chloroalkane. And then we divide it by the MR of all the products. You could also do divided by the MR of all the reactants. It's the same, but as we already have to work out the MR of the product, of one of the products, I always think, because of the conservation of mass, why on earth would we not just use all of the products for the next part of the calculation? Speeds us up a lot. So because we want it as a percentage, we're going to times it by 100. So the MR of the useful product here, so the MR of this C5H11Cl, is going to be 5 times 12 plus 1 times 11, so just 11, plus 35.5, and that there will tally up to give us 106.5. So the MR of our useful product is 106.5. And then we divide it by the MR of all the products. So the other product here is HCl, which is just going to be 1 plus 35.5, so 36.5. So on the bottom, the MR of all those products is just going to be 106.5 plus 36.5. And see how quick that was? That's quicker than working out the MR of all of the it's quicker than working out the MR of all of the reactants there. So putting this all together here and then timesing it by 100 to turn it into a percentage, I end up making that 74.48%. So our answer there is A. Okay, so 2-methyl-2-butene reacts with HBr to form a mixture of two different products. We're asked to name the type of mechanism involved in this reaction. And normally at this level, if they ask for the mechanism, it's going to be one of three things. It might be electrophilic addition, nucleophilic substitution, or it could also be free radical substitution. And in this case, because we're talking about an alkene reacting with HBr, it's going to be an electrophilic addition reaction. And that's something that we really should just recognise, that if we're reacting a CC double bond, an alkene bond, with a halogen or even things like H2 or HBr, it is going to be electrophilic addition. So now we're asked to draw the structure of the 2-methyl-2-butene. They haven't specified here if they need it as skeletal or as just structural. So here I'm going to do it in the way that I personally prefer. Butene, 2-butene. I'm going to start by doing a chain of 4 carbons, because that's the longest carbon chain, referring to that but, which is 4. And it's 2-butene, so on the second carbon I'm going to put my CC double bond. And then we know it's 2-methyl. So also on the second carbon, we're going to have a methyl group coming off of it. So here then, if I fill in the rest of the hydrogens, I will have my bond nicely completed. So I'm going to fill in H's everywhere else. And then I'm going to have the correct answer to this, 2-methyl-2-butene looks like. You may see that written in different ways, depending on if you've chosen structural, skeletal, lots of different ways. But so long as everything's in the right position, then your answer will be correct. So don't worry too much. They haven't specified, and that is really the thing you want to be looking out for. Have they stated how they want you to do the structure? And if they haven't, use the way you're most confident so that you do get those marks for sure. So here we're told that 2-methyl-2-butene doesn't have EZ isomers, but a structural isomer of it does have EZ isomers. We're asked to draw the structure of the Z isomer and write the name for it. So if we start just by sort of writing it out again. So just sort of filling in some carbons. We can see that this doesn't have EZ isomers because it has two of the same group coming off of one of the carbons. And the definition for having these EZ isomers or cis-trans isomers is you need a CC double bond and you need 2 different groups coming off of each of those carbons of the CC double bond. And we don't have that here. So we need to think, well, what can we do then to make sure that we do actually have EZ isomers. So I would suggest here that probably the easiest thing to do would be just to write it, not as having a branch with a carbon coming off of it, just thinking, well, in total here I have 5 carbons. So let's draw a 5 carbon chain, and let's put that double bond, let's say, on the second carbon. And if we sort of fill in all of the hydrogens here, end up with this particular case here, and I can see I have different amounts. I have 2 different groups off of each of those carbons, so we're looking golden here. I'm going to simplify that here because I've been lazy and not written all the H's there, but I'm going to write CH3, that's from there. I have got this H jutting off down here, that's from here. The CC double bond, this is the first carbon of that CC double bond. And then this guy here is the next one. So these are the carbons of the CC double bond. And then I can see over on the next one, I've got an H, and then I've got this C2H5, okay? I'm going to do the same there. I'm going to have an H and then a C2H5. And so I've drawn it like that. Whenever I need to draw EZ or cis-trans isomers, I like to draw it in that format with the CC double bond in the middle and then everything branching off of it. So it looks a little bit sort of like how you would normally draw ethene. Obviously it's not ethene. But here, because they want the Z isomer, but that's the same as a cis isomer. So here they're on the same side. I've already actually drawn it. So the answer is I'm going to have basically Z, because it's Z isomer. It's going to be pent 2ene. So we had that CC double bond in the middle there. It's just a 5 carbon chain with that carbon double bond on the second carbon of that chain. So next, the question kind of goes back to now that 2-methyl 2-butene, which, let's remind ourselves, was this guy here. And we're asked to draw the major and the minor products. So if we go back to our original drawing, and I'm going to fill in all the hydrogens just so we're really, really clear on what's going on here. We need to remember that when we have something like HBr, we get the major product when the bromine attaches to the carbon of that CC double bond. So which of these guys is attached to more other carbons, okay, rather than hydrogens. So the major product out of these 2 options, so let's call them option 1 and option 2, the major product is going to be the one where the Br of the HBr attaches to carbon number 1. Because that carbon, you can see it's got 2 CH3s attached to it. Whereas number 2 has an H and a CH3, which is going to make that the minor product when the bromine attaches to that carbon, because that carbon has fewer carbons that it is attached to. So here, if we had to draw those products, so I'm going to write major here, and I'm going to write minor here. We know that both the H and the Br will attach to it, and it's going to break that double bond. So we don't have the double bond anymore, but we know that the major is going to involve the bromine attaching to that carbon, which has the 2 different methyl groups, which in our labelled diagram earlier was carbon number 1. So we need to fill in all of the H's everywhere else. Of course, what we have done, just to highlight it, is we've added a bromine and an H, and we've split open that double bond, but the decision maker for if it was major or minor was make sure the bromine goes onto the carbon that is attached to as many more other carbons as possible. So for the minor, we're going to draw it almost exactly the same, with the exception of that H and the Br that I've highlighted there. They're going to be the other way around. So as you can see there, they're the other way around. So next we're asked to draw the structure of the intermediate that led to the formation of that major product in the reaction of 2-methyl 2-butene with HBr. So this is almost just sort of going back to what we thought the answer was. So remember we said that to get the major product, you needed to have the bromine attach to the carbon attached to the more carbons. So let's draw this out now. So we knew that there was a CH3 coming off of here. We know that there was another CH3 here, an H here, and a CH3. And we said that the first thing that's going to happen when we break open that double bond is the hydrogen will attach here. And in doing that and breaking that double bond, we form we form a carbocation just here. And that there is our intermediate. The name of this type of intermediate is we have a tertiary carbocation. Tertiary carbocation. Or you could also say, as your answer here, a tertiary carbonium ion. And if you're wondering why it's tertiary, it's because this carbon here has 1, 2, 3 different carbon groups attached to it. Well, that's brilliant. Well done for getting through this question. Begins with a chemist carrying out an investigation on the equilibrium system shown below. So we're given some information here and we're asked to predict what changes might happen on the position of equilibrium and the rate of the backward reaction when we do a couple of changes, okay? So here we can see that the temperature we are going to keep the same, the pressure we are going to also keep the same, but we have a difference here. Initially we used a catalyst, but now we do not use a catalyst. So here we need to predict those changes. So for the position of equilibrium, we're going to say that there is no change. And the reason why there is no change is because equilibrium doesn't do anything to affect that position of equilibrium. It's not going to shift to the left or to the right. All that it's going to do is to speed up the rate of the forward and the backwards reaction, but by the same rate. And that's going to give us our explanation for part 2. So when we do not use a catalyst, the rate of the backward reaction is going to decrease. And the reasoning for that is, again, when we have dynamic equilibrium, the rate of the forward and the backwards reaction are equal. Okay, so if we change this rate by, say, not using a catalyst, then that reaction is going to take place slower of both the forward and the backwards reaction. Perfect. Let's try the next question. 10 to the minus 3 moles of Y in a 1 decimeter cubed container. At equilibrium, the mixture contains 3 times 10 to the minus 4 of X. So we can see that the amount of X has gone down. Now we're asked to calculate the equilibrium constant, Kc, including units, if any, for the equilibrium. And we want to give our answer to 3 significant figures. So first things first, let's write down the equation that we had on the previous page, because we need to use that here. So because this is an equilibrium question, I'm going to use my ICE method. And I use this just to help me lay out the information and get everything that I might need. I like to separate the products and the reactants with like a little double line just so that I can clearly separate them in my head. And I'm going to start now by just filling in the information from the question. So I know that I've got 2 times 10 to the minus 3 of X. So I'm going to fill that in. I also know that I have got 4 times 10 to the minus 3 of Y. It's important to note that we have a 1 decimeter cubed container. That's important because as it's 1 decimeter cubed, that means that the moles, the number of moles, is actually going to be equal to the concentration, because concentration is moles divided by volume, and in this case the volume is just 1. So in this specific case, the moles we can use as the concentration. So I think it's fair to assume from what they've said that we didn't start with any Z at all, so we're going to put a little 0 there. And we're told that at equilibrium, the mixture contains 3 times 10 to the minus 4 moles of X. And we're told that at equilibrium, the mixture contains 3 times 10 to the minus 4 moles of X. Okay, so we can see there that it's gone down. And this is where our ICE table comes into it. So it has gone down by a certain amount. We need to work out, well, by how much? And the change here is 1.7 times 10 to the minus 3. So that's how much it has gone down. Now we can use that change to work out the amount at equilibrium of both Y and of Z. So all of the reactants are going to go down by that factor and up by the same. So an important thing to notice here though is that we have 2 moles of X but only 1 mole of Y. That 1.7 times 10 to the minus 3 that it has gone down is representing 2 moles of change. But Y is only 1. So what we want to do there is to halve that amount and to instead now subtract half of 1.7 times 10 to the minus 3. So that here is going to be 8.5 times 10 to the minus 4. Now that is what it is going to go down by, which is going to leave you with an equilibrium amount for Y equal to 3.15 times 10 to the minus 3. Now over on the other side, because those are the products and the products are what we're making, it is going to go up, and because it is 2z, just like there were 2 x's, it's going to go up by 1.7 times 10 to the minus 3. So 0 plus that amount just leaves us with 1.7 times 10 to the minus 3. So we have all of our equilibrium amounts. It's worth just pointing out there that all of those relate to the moles. If this was a different type of question and say the volume wasn't 1, we would then want to work out the concentration to find Kc. But because this is just 1 decimeter cubed of volume, the moles is the same as the concentration. So now we've got this, what we can do is to say, okay, so Kc equals, and it's the concentration of the products to the power of their moles divided by the concentration of the reactants to the product to the power of their moles. So the equation for this case would be the concentration of Z squared over the concentration of X squared times by the concentration of Y. And in this case, we will put in the right numbers. So we've got 1.7 times 10 to the minus 3 squared all over 3 times 10 to the minus 4 times by 3.15 times 10 to the minus 3, and forgotten to square this, squared. Okay, so now that we have that there, we will put that into our calculator and out will pop an answer. And to 3 significant figures, which is what was stated that we wanted, I get 10,200. So my Kc is 10,200. And of course here we want the units as well. And to work out the units, we go back to that formula that we had for Kc. But instead of inserting the numbers, we're going to insert the units. And we will see if there's anywhere where we can cancel things out and simplify. This basically turns into a little bit of algebra. So here I can see that on both the top and the bottom is moles per decimeter cubed squared. So I'm going to cancel those out, and that leaves me with Kc equals 1 over moles per decimeter cubed. Because both of those are on the bottom of a fraction, we don't really give units like that 1 over something. We want to rewrite it, and the powers of anything on the bottom of the fraction, their sign is going to be changed. So at the minute it's like mole to the power of 1, we're going to make that mole to the minus 1 and dm cubed. So the answer to this, the units, would be mole minus 1 dm cubed. Perfect. Here we're told that the student investigates a reaction between dinitrogen tetroxide, a colourless gas, so it's going to be N2O4, and nitrogen dioxide, which is a dark brown gas, it tells us. And we're told that the energy change of the forward reaction is a positive enthalpy change of 57 kilojoules per mole. And we're told that once an equilibrium is established, the reaction is cooled, okay? So the temperature is going to be decreased. And we're asked to describe what you would expect to observe. Well, because the forward reaction is endothermic, it means that the backwards reaction is going to be exothermic. And if we were to cool down the temperature, then that means that the reaction is going to shift into the exothermic side, which means that we're going to end up shifting from having this dark brown gas to having more of this colourless gas. So as a result, because we have this endothermic and exothermic reaction, we're going to see that this reaction is going to favour the exothermic reaction, and therefore we're going to make more N2O4, and as a result the mixture will get lighter in colour. You'll still have some of the NO2, so it's not necessarily just going to go colourless, but it will get lighter. So the student decides to carry out the reaction at a higher pressure. So let's imagine the pressure is going up. What happens to the rate of the reaction. Now I guess if we look at the earlier reaction and balance it, we should always balance. We can see that we've got NO2 goes to 2 NO2s. And that would matter if this was asking about the position of equilibrium. But this question is not asking about the position of equilibrium. It's asking what happens to the rate. And whenever we're asked a question about the rate in an equilibrium question, it's kind of irrelevant to the fact it's an equilibrium question, because all we need to know is when pressure is increased, the rate of reaction will increase. And that is just due to particle theory, collision theory. If we have a higher pressure, we're going to have more crowded particles, and therefore we're going to have more frequent successful collisions. And then the consequence of that is that the rate goes up. And that there would be our explanation for B. Okay, so this question is based on the substances A, B, and C, and we're asked to name substance A. So here, the very first thing I would potentially do is draw it out, but in fairness, it's probably clear enough as it is. I would draw a line through the longest chain of carbon atoms. And here I can see that I have 4 carbon atoms in a row. And I can see that amongst those I have a butene because I have 4 carbons. So I can say that I have but1ene there because if we number those carbons, I can see that the double bond is attached to the first carbon. And then I can also see I have a methyl group, and I can see that that is branching off of the 3rd carbon of that chain. So I can say that here I have 3-methyl but1ene, and that there is going to be the name of our substance A. So now we're told that that same substance A reacts with HBr, and we're asked to draw the structure of the major product for the reaction of A with HBr. So I would start now just by writing it in a more familiar format. So I'm going to write it like this. I can see that there's 2 H's coming off of the right carbon of that double bond, and on the other side I have an H coming off of that second carbon, and also I have a CH3 2. Okay, so there I can see I've got that branching. And the important thing here when it comes to determining which is the major or the minor product is what position is the bromine going to attach to? Is it going to attach to this carbon here, which has this group attached to it? Or will it attach to this carbon which doesn't have any groups attached to it other than just hydrogens? And the answer here is that in the major product, the bromine or the halogen, whatever halogen it is going to attach to the carbon of that CC double bond that has the most other groups attached to it other than hydrogens. So in this case here, my major product is going to have the bromine attached to this carbon which has the CH3 attached to it. And on the other carbon, that's where the hydrogen will go. So this here is our major product. If they also wanted the minor product, I would just reverse this bromine and this hydrogen, and that would give us our minor product as well if we needed it. Okay, so here we're told that substance B can be polymerized to form polymer X, and we're asked to identify the polymer X. So here they just want us to identify it, which means they just want us to name it, basically. So the first thing to do is to name what that monomer is that they have, okay? And that monomer would be phenylethene, okay? So the polymer version of that is going to be polyphenylamine. So just make sure that you're confident in naming substances like B, so phenylethene, so that's called phenylethene, and so the polymer would just be polyphenylethene. So for 7.4, we're told that substance C can be polymerized to form polychloroethene, and we're asked to show a balanced equation for this. So when it comes to the monomer of this, that is just chloroethene. And when it comes to writing a balanced equation for the formation of a polymer, we want to put a little N in front of it. And then what that will become is something where we break open that double bond so that it has nice little open arms. Everything else looks exactly the same, but we're going to add in some brackets around it and a little N down on the bottom right hand corner. And so that there is a formation of polychloroethene from simply chloroethene. Perfect. So that there is now the end of the paper. So well done for getting through this. I hope it's helped you understand lots of this AS work and you're feeling a lot more confident now.
Ouch! This is why in some videos I'll explain scratches.